Now, let's talk about another practical issue with our op-amps. They don't have infinite gain. In our ideal models, we assume the gain is infinite, but in reality, it's just very large. This is what we call finite op-amp gain, and it introduces a specific type of error. Look at the equation for the residue voltage, Vindersus. It's a bit more complicated now. The denominator is no longer just the feedback capacitance, C_. There's an extra term that is divided by the op-amp's open-loop gain. If the gain were infinite, this entire term would go to zero, and we'd be back to our ideal equation. But since it is a finite number, this term is small, but it's not zero. So what's the effect? This extra term makes the denominator larger than it would be ideally. And when you divide by a larger number, the result is smaller. This means the actual residue voltage, V_, will be smaller than the ideal residue voltage. In simple terms, the gain of our ADC stage is less than we designed it to be. You can see this effect very clearly in the residue plot on the right. Ideally, the peaks and valleys of this sawtooth waveform should reach all the way up to plus V down to . However, because the gain is lower than expected, the output signal gets compressed. The peaks don't quite reach plus V, and the valleys don't quite reach V, as highlighted by those purple ovals. The entire output swing is reduced. Now, what's the consequence of this compressed residue signal? Remember, this V_s becomes the input for the next stage in the pipeline. The next stage is designed to handle an input that swings between plus V_r and V_. Since the signal it's receiving is smaller, it won't be able to exercise its full input range. This means the subsequent stages can't produce all of their possible digital outputs. When you combine the bits from all the stages, you'll find that certain final digital codes can never be generated. This is what we call missing codes. So, finite op-amp gain is a direct cause of missing codes in a pipelined ADC.